Hello, today I will be teaching you about 8.3 power series. Your first question would be, what's a power series? Well, power series is essentially an infinite sum defined by this. It is the sum of n equals 0 to infinity of, I have written alpha n, essentially that's just a coefficient, x to the n. Now, there's a few key definitions you need to know beforehand. These definitions are essentially mandatory to be able to understand what's going on, right? To start, the interval of convergence. So, interval of convergence, it's pretty much on the nose what it is. It is the interval in which the series converges. Now, that can take many shapes, many sizes. You could have the interval from -2 to 47, 5 to 20, whatever numbers. In between those numbers is where the set converges. Now, there are a couple exceptions, such as r, which is our radius of convergence, which essentially is just 1/2 of the length of the interval of convergence. So that's a pretty simple thing to understand. Essentially, you have your interval 1 to 4 or 1 to 7, the direct center of that is your radius of convergence. It's your midpoint, essentially. That's why it's defined as 1/2 your interval, because you have your interval, say your interval is this big, your radius is right here in the middle, because it's 1/2 this. Same way if your diameter to radius in a circle, your radius is just half your diameter, right? It's half your left to right overall size. The exceptions come in is that when r, which is your radius of convergence, is equal to 0, the series converges only at 0, which makes sense, right? If you're centered at 0, your interval can't be very, very large. Now that you'll get more into, I'll explain that more in depth whenever I start going over the examples. And when your radius of convergence is infinity, all real x is where it converges. Makes sense. If your midpoint's infinity, well, obviously your high end's got to be infinity. If your midpoint's infinity, your low end's got to be negative infinity. So all real x is where it's going to converge. Now, let me get into some specifics. The first way that you go about solving a problem, say you're given a series, and it's like, hey, I need you to find the interval of convergence and the radius of convergence. Well, the first one to go through is lim sup. That is the first method of solving for it. Essentially, lim sup, limit supremum in approaches infinity of alpha n, which is just your coefficient. So say you're given an example like this. This is a good lim sup example. X minus 1 to the n over n in the series n equals 1 to infinity. Your coefficient is going to be 1 over n, because the coefficient of the top term is 1, bottom term is n, which is coefficient. So 1 over n is your coefficient, right? That's what that alpha n represents. So in that example, this would look like 1 over n raised to 1 over n. Now, let's get to an example of what I'm talking about. And I've got the craziest thing to show you. The example I'm thinking of is the one I just showed you. A little movie magic for you. X minus 1 to the n over n, as we just discussed, means that the coefficient is equal to, coefficient is equal to 1 over n. Now, you're asking yourself, what do you do at that point? Okay, what do you do when your coefficient's 1 over n? Where do you go next? Well, this is when you move on to step 3, where you take that 1 over n and you apply it directly to the lim sup equation, right? So, when applied directly to the lim sup equation, 1 over n raised to 1 over n is 1. Lim supremum as it approaches infinities of 1 is 1, right? So the conclusion you're going to come to is that your alpha equals 1, right? Because lim sup solves for alpha equals 1. Now you're asking, alpha equals 1? How does that help me find r? How can I find r knowing the coefficient's 1? Well. I've been holding out on you because I've got a little cheat sheet right here. So, power series, there's a couple rules. When it comes to lim sup, these are our true rules given the exceptions I mentioned earlier. So, r equals 1 over alpha, infinity, or 0 when alpha is either in between 0 and infinity, alpha is equal to 0, or when alpha is infinity, right? So now that I'm knowing that, alpha equals 1. What does that mean that r equals? That's right, 1 over 1, or 1. Now, you're asking yourself, what does that have to do with it? How do I find the interval, though? You know, I know r equals 1, so my radius is 1, but, you know, what does that mean? You know, my interval could be anything from 47 to whatever, as long as 1's in the middle. No. So, your r is equal to 1. Your radius is 1, meaning that your thing can only be 2 wide, right? And now, an important thing here is where it's centered at. So, I omitted a little bit of something here. In the textbook that you guys go over, it doesn't include this, but typically this equation has a couple ways of being written. One of which is alpha to the n x minus c n. That minus c is your center point. So for this specific problem, the center point we know to be 1 because that is where the initial equation is. It's n equals 1 to infinity. Here, n equals 1 is the center because of the power series given. That's how you know that in this given instance. So, since your center is 1 and r equals 1, you take that center of 1, add 1, get your 2, take away 1, get 0. So your endpoints of your interval is from 0 to 2. You don't stop there. All that means is that you know your interval, but you don't know a key thing, and that's whether your interval is open or closed. You'll never guess. I've got a solution for that. It's called plug it back in. So, you take the 0 and you take the 2, and you plug it back into that original equation, right? When x equals 2, you get the series 1 over n, which diverges. And when you plug in x equals 0, you actually get the series negative 1 to the raised to the n over n, which is an alternating harmonic, so it converges. Which means, as you can see there, with that nice little bracket, that it's closed on that side of the interval. Now, because it diverges at 2, it's open. So that can tell you if it's closed or open. Now, moving on to the next theorem we discuss. Ratio test 8.3.6, also defined as ratio criterion. The radius of convergence r of a power series, this is the original power series I showed you at the beginning, is equal to the limit as n approaches infinity of alpha n over alpha n plus 1 absolute value of that, which I have right here to show you. This is what I just said. So we know r equals this, provided the limit exists. That's the key point. The limit has to exist for us to be able to apply this, okay? So if you're given a power series and you're like, oh, how do I solve it? How am I going to approach this? Well, the lim sup that I showed you right in the beginning, you can apply that to anything, right? Typically, that's your go-to, that's like your workhorse. But when you look, you might look at a couple power series and go, that looks real ugly. I need something easier. The limit exists. Well, That means your go-to guy, if the limit exists and it looks a little ugly, should be ratio test. And I'll show you why. So, given an example such as this power series, n equals 1 to infinity of x to the n over n 2 raised to the n. Okay? I don't know about you. I don't like the way this looks. This looks kind of ugly to me. I don't want to use lim sub. So, let's use ratio test. Also, because wouldn't be learning much if I only showed you one thing, would you? So, what we're going to do is how we start all of these ratio tests slash power series problems. Define your coefficient. In this, your coefficient is 1 over n2 raised to the n. Now you might be saying, what? Why does my coefficient have all of those terms in it? Well, the coefficient, as I showed you earlier, I wrote as alpha n in this. Really, it's a n, anything n, right? I chose alpha as my, essentially, like, insert variable n. And so n is included in all of it. The reason up top we don't include it is because it's only here as a power to this, which has a coefficient already. The coefficient in front of our variable is 1. Down here, we don't have a variable. We just have a coefficient, essentially. We have the n term. So our coefficient is 1 over n2 raised to the n. Now, let me just show you. See? Alpha lower n equals 1 over n2 raised to the n. From there, we move to step 3 in the process. Applying the power series. So now we have to take this and actually plug in our coefficient to it, which is shown here. So it's going to look a little ugly. You know, you have a fraction over a fraction because the power series, or not power series, the ratio series uses a fraction already, and so you're running this fraction into this fraction, right? Now, notably, I did omit the absolute value bars because all of our values here were positive. Those are necessary. I just chose not to write those in here because the positivity of the equation I did not think called for absolute values to be written here further. And so keep in mind the absolute value bars do exist there, but I did not write them. So 1 over n2 n over n plus 1 to raise to the n plus 1. Because if you notice, that bottom term right there is alpha lower n plus 1. And it's similar to when we did induction proof, stuff like that, and you would take your value and you would apply n plus 1, so all of your instances of n would be replaced with instances of n plus 1. We're doing that again. So we take that n plus 1, boom, boom, and now we're going to move to a simplification step. So this can be simplified by flipping the bottom fraction, multiplying it times the top, which is going to give you, n plus 1 to raise to the n plus 1 over n to n. From there, you can cancel out a couple terms, and it simplifies down just a little bit more to 2n plus 1 over n. Then move further down to 1 plus 1 over n, because n over n is 1. 1 over n is what you're left with. 2 times that, you can take the 2 out. Okay, limit of this now. Its limit as n approaches infinity. Didn't write that. Its limit as n approaches infinity. So as n approaches infinity, 1 over n approaches 0. So you can effectively treat that as 0. 2 times 1 is 2. So limit of 2 is 2. Right? Which means that your radius of convergence is 2, because unlike in the lim sup where you're getting the value of your coefficient, here you're getting the value of your radius. So your radius of convergence is the answer to these. So radius of convergence in this given example is 2. But if you recall, you're not done when you find your radius of convergence. From there, you take your endpoints, which it's centered on 0 here. So your endpoint's going to be 0 plus 2, 0 minus 2, which is going to give you the interval -2 to 2. So your interval convergence is -2 to 2. But, as in the first example, we're not quite done yet. We have to apply one more step. That one more step is to then take your values and plug them into the original problem to then get your new values. So, your original problem looks something like this. So you're going to plug in for x 2, and then you're going to plug in -2 for x. So 2 raised to the n over into n, you're going to end up with 1 over n, which diverges, and then -2 raised to the n over into n, you're going to end up with -1 over n, which -1 raised to the n over n happens to be another alternating harmonic, which means it converges, and since it converges, it's actually closed again on the lower end. So it's closed at -2, and then at 2, it's open. Now, that was intentional. Just so happened the examples I was showing you guys today had 2 alternating harmonics, which caused it to converge and be closed on that end. Okay, so moving on. Overall power series, it's a very simple thing. I think a lot of people can use. It has some pretty good ability to find these intervals, find these radiuses, and go further. Now, let me pull this back up. I mentioned this earlier on. This can be used as a very helpful idea when it comes to thinking of these, because obviously I mentioned it converged or it diverged. I don't think I explained enough what that means in this context. So if it converges, that means that the absolute x is less than r. If it diverges, the absolute x is greater than r, right? So say you go through and you get an r equals 4, and your original thing is like x over 1n or something like that, right? Well, it's like something where your x becomes greater than your r. That's going to diverge. That's the most common occurrence, is your x is greater than your r, so it diverges. That is unless, now, to be granted, I'm saying all this as in terms of unknowns. You have these unknown values and you're figuring out these things. Reality is, once you find your interval, you know where it's going to converge and diverge almost always. If your interval is from -10 to 10, right, and I give you the number 5 to plug into it, it's going to converge because 5 is within your interval, and it's called the interval of convergence because it converges in the interval. And the same can be said with diverging if I give you a number outside of your interval. So overall, power series, very simple, nice topic to discuss. Much simpler than I think I was led to believe when I was going into it. I think you guys as a class can really enjoy this and can apply it a little further on. Let me fluff out my notes. So, in general, the biggest takeaway I want you guys to have from this class is the ability to apply these power series and understand, be given a power series, I want you to be able to look at it, tell me what to do, apply it, and an ending, I want a radius, and I want a interval of convergence. So due next week is your guys' homework on this, 8.3 power series homework. I think it's 7 problems over seven examples where you choose which method you use and you apply it, but you have to at least do 3 of each, because some of them you can use either method. At least 3 of each. 3 of each, and then problem number 7 is a bonus. You know how I like to do my homeworks. It's a little bit harder of a problem, but it's an extra little special bonus for you guys if you think you're up for the challenge. And with that, oh, that's the bell. All right, guys, I'll see you next time.